Sorry, there is a there is a prom going on and the house is in commotion now. But number 29. Oh, there's my class sheet. There you go. Number 29. If relativistic effects are to be less than 1%, then gamma must be less than 1.01. At what velocity is... Oh, that's simple, right? So just, yeah, gamma is 1 over square root of 1 minus u over c squared. Okay, so then you find the velocity. Okay, let's go to length contraction. We have a spaceship that is 200 meters long. I see on board. So this is important. I see on board, it means we are talking about proper length. So somebody on board, right, went there and carry along the corridor of the spaceship. Imagine the spaceship like this, something like this, right? So somebody there went from here all the way there with a ruler and measured 200 meters. So this is your point A, this is your point B. We are talking about proper length. And moves by Earth with a given speed. What is the length measured by an earthbound observer? So now, how are we going to see that? Length contraction. L is equal to L naught square root of 1 minus u over c squared. Okay? And then you apply the formula. So this is your proper length, which is 200, and this is what we see. So we see the spaceship slightly squished. Okay? How fast would a 6-meter long sport car? So 6 meters, somebody did that, right? We are talking about proper length. Have to be going past you in order for it to appear. Oh, that's how you see it, 5.5. And you apply your equation. See, relativity is simple. It is simple as long as you know what is proper length and what is proper time. Now, how far does the muon in example in example 5.5 wait a second. How far does the muon in example 5.1 travel according to an earthbound observer? So 5.1, so we have to go to 5.1. Hate those. What? This is not a muon. 5.1. I think we can do it. But I remember, oh, that's the muon here. Okay, so we have a muon. We have a muon. The velocity is 0.95 c. And then leaves as measured in the muon's frame of reference. So T naught. Let's get that information. T naught 2.2 10 to minus 6 seconds. This is important. Okay, so you have to be able to read the problem and then figure what is what. And the problem is still going on here. And I'm here in relativity. Isn't that all relative? People are downstairs are happy, excited, drinking champagne, and I'm here putting this video. What a life. Okay, so what is the question? Blah, blah. What is the length measured by an earthbound observer? So an earthbound observer So is length, no, wait a second, what am I doing? Oh no, the muon. Um, how far does it, oh, so we want to find the length as observed by somebody on Earth. So how do we do that? So the length is equal to the length observer in the muon rest frame. Do we have that? No, we don't. We have the proper, um, well, we can do something different. We can use laws of physics. So we have the proper time, so we can find the proper, the time observed by somebody on Earth. The time observed by somebody on Earth is equal to the proper time divided by 1 minus u over c squared, right? And then we find the time, which is going to be something bigger than 2.2 10 to minus 6. So once we find the time, oh, come on. Once we find the time, then we can find the length. The length is equal to the speed times the time, right? The time. So this is an observed. This is Chris, right? Chris is doing his muon thing, and then he knows the muon is going to leave this much seconds. He knows the speed, and then he finds the length. Since the muons produce up the way down in the atmosphere, so it's going to be 0.95 c times the time you calculated up here, right? So in this time calculated up here requires this number, and this requires the u, which you already have. And then you convert c to 300,000 kilometers per second, and then the work is done. B, this is part A. Part B, how far would it travel as observed on Earth? Isn't that what I just did? Oh, how long? Oh, how long? How long is t? We did, right? And how far is L? We did. See, what distance is this in the muon frames? Oh, the distance is simple. The distance is the proper length. That is equal to 0.95 c, the speed, times the proper time, right? And then you get your L naught. And okay, good enough. So I think that's it. Lorentz transformation, I'm glad I went through, but you guys were not excited. After Mark's um, comments, I decided not to go further. No, just kidding. Okay, that's it.